Don't even.
Come on.
I've not yelled at Kevin like I've yelled at the three of you.
What?
Wait, what
Oh.
have we done?
Jacob's innocent.
I'm
Guilty.
AP, not in AP Physics, no.
I haven't done anything wrong today.
Colin, you just shush. Okay, so visualize this. You've got a beaker with 20 milliliters of a 0.15 molar solution of iron 2. I'm going to add hydronium ions. Why? Make it magic. Maybe make it acidified, I don't know, or magic, either one. And then I'm going to titrate that with MnO4. So what color is MnO4?
Purple.
Very, very bright purple. Okay?
I don't know. We have to know that for the test.
You did this lab.
I don't
Oh,
think
that was a
that's
while ago.
Yeah.
It's the tasty looking lab.
You know everything.
If it takes 12.6 milliliters of the MnO4 to reach the titration point, what's the molarity of the MnO4?
Well, I mean, I could do it, but like you gotta balance.
Your face did.
And then
Your face said, I have absolutely no idea.
It's been a long day. It's been a long week. It's been a long life. This feels new.
Okay,
This is really good titration.
Yes.
I have a day and a half left.
it's stoic.
This is bad. This is really bad.
Okay.
I'm tired this week.
Starting with
Oh.
milliliters.
I'm so tired.
Now,
The balance equation.
so let me ask you this.
No.
We're just gonna start.
Let's start with this idea. When you have Fe2
I'm
plus,
locked.
what are the two things you can do with Fe2 plus?
You can go to iron or you can go to Fe3 plus.
You can make elemental iron or you can make Fe3 plus. Okay? So one of these two is going to be the product, right? Either elemental iron or Fe3 plus. So let's just start that thought process. Okay? Ooh, what'd you say, Addie?
Oh, I just didn't know that we had iron in the first place. I see now.
My bad. I should have written that.
I thought we just had the MnO4 and I was like, it's gonna be MnO4.
No. In the beaker, we have Fe2 plus.
Yes!
What? Get out!
This is the whole point.
When did you sneak that up on the screen?
So excited that you were going to answer.
Okay. Now, visualize what's going to happen. You're going to add the MnO4. MnO4 is a very, very dark purple, right? Okay? Very, very dark purple. So, if the Fe2 plus is still in there and can react with it, the MnO4 is going to get used up. But if there's no, once the Fe2 plus is used up and you add more of that very bright MnO4 to it, what's going to happen?
Dark purple.
It's going to stay that color. So it's going to stay that color because you don't have any Fe2 plus to react with it. So that's how you know you've reached the point, because MnO4 is a very, very bright color. You don't need it to really understand the problem, but that's the visual that you would have. So as long as there's Fe2 plus in there, the MnO4 is going to get used up. Once the Fe2 plus is used up, hey, the MnO4 is just going to stay there and it won't react. Okay, we can only do that with something that has a very distinctive color like the MnO4. Okay, now let's talk about the MnO4. When you have MnO4, and again, when you go to answer this, understand on the test you're going to have that blue sheet and you're going to have that white redox chart. Is MnO4 a good reducing agent or a good oxidizing agent?
Oxidizing agent.
How do you know?
It wants to be reduced.
Okay? Because where's it at, Gatshon? It's towards the top, right? So what's the charge on the manganese ion in MnO4? Plus 7. You have 4 oxygens at -2, that gets you -8. That means that has to be plus 7, so that they all add up to -1. Now think this through. If you say, well, I think I'm going to make iron, okay? You think out of this reaction, one of your products is going to be iron. So the Fe2 plus would be oxidized or reduced. It'd be reduced because you would change that into Fe. So if that's reduced, what would the manganese have to be? Oxidized, which would mean it would have to lose even more electrons and turn into like Mn9 plus. Do you ever see Mn9 plus?
No, that's crazy.
No, because it doesn't exist. Mn7 plus is as far down as we're going to go. And even then, that's a big deal because of the fact that it's like a pendulum, and that Mn7 plus is way over here on this pendulum side. It's lost 7 electrons. What do you think it really wants to do? It wants to gain electrons. Now,
Sorry.
Sorry.
you have 2 tests for me to take.
Please don't fail me. Please don't fail me.
Do you really want me to be in Cohen mode when I grade your test? I'm about to get there.
I really dislike that I have my own mode named after me, and I dislike more that it's a bad mode to be in.
I was just irritated. But did you see why I'm irritated when I grade? It's like Cohen. Like, look at the paper that I just gave back. What did you not write on the front of the paper?
His name.
My name.
Yeah, because he's
Right away.
Okay, wait.
He
I wrote
stole
on the
my
actual-
paper. He stole
Silver is
the
the
top
color,
pages
like
of my
I
paper. I
accidentally
used
green,
his
blue.
paper and write my name on it.
It was an honest mistake, and I did write my name on the assignment. It wasn't like I turned in another assignment with no name on it at all, which has happened.
That just means the color.
Like a red substance, a yellow substance.
Okay. So, since we're not, how would you, the other thing, how would you know if you made elemental iron? What would you see? You would see chunks of iron in the bottom of the beaker. Have you ever, in any reaction that we have done, have you ever seen chunks of iron form up in the bottom? No. So what does that mean it's going to make?
Fe3 plus.
Fe3 plus. Okay? So the Fe2 plus is going to turn into, Cap Sean, where am I going to put the electron? On the reactant side or the product side? Why?
Because it lost an electron for P plus.
Mathematically, why do I need to put that over there?
Oh, yeah, that's true. Yeah, that was a.
Oh, to balance the charges. Otherwise known as the Gap-Sean step. Now, you have the MnO4. Back up.
Whoa!
I have-
Make a smiley face at that.
You got your MnO4. Now, that's 1 minus.
Was.
1 minus.
That's MS9.
So the problem with Mn7 plus, it can go into Mn5 plus, 4 plus, 3 plus. In this situation, where are you going to end up?
Probably some water somewhere, so.
2 blood.
2 plus, okay? Because if you look on that white reduction chart, you have this equation. Unless I explicitly tell you differently, you assume that that ends up at Mn2 plus, like the pendulum swings completely over here to Mn2 plus. So when you see MnO4, unless I explicitly tell you that it ends up at Mn3 plus or Mn5 plus, you just assume that it goes to Mn2 plus, okay? Now, we need to balance it. I got 4 oxygens. What am I going to do, Graham?
What?
How can I balance 4 oxygens from the MnO4?
You're gonna have 2 O2s on the other side. What? Oh, you're gonna make
We're
water?
doing great.
Yeah.
How many?
4.
Oh, yeah.
Hey, the test isn't to the one, so I'm fine.
And physics.
Now, I have 8 hydrogens on the product side. How am I going to get 8 hydrogens to balance that?
That's not the same thing.
Am I going to put 4 H2s? Or am I going to put 8 H pluses? Because if I put 4 H2s, I have no chance of making it balance. Okay?
See, I respect.
So I've got that.
That was like 3 questions.
Even though we need.
Is that done?
No.
What else do I need? Electrons. So Mn7 plus and Mn2 plus involves 5 electrons. Where am I going to put them? Reactant side, product side. Reactant side.
5 big fools.
Now, at this point, if this is right, how do you know it's right? I take 8 plus and 1 minus, that gets me 7 plus. And then I got 5 negative charges, which gets me 2 plus. What's the only thing that has a charge over here? Manganese. Are we good?
Perfectly good.
So, what am I going to do with this up here? Multiply by?
5.
Why?
Electrons cancel.
Electrons cancel.
Remember when we did this?
Oh,
Yay!
okay. So I've got 8 hydronium ions plus MnO4 plus 5 Fe2 plus 5 Fe3 plus plus Mn2 plus 4 waters. At this point, could you calculate the E naught value?
Yes.
How?
Look at the chart.
Look at the chart. What's the E naught value for the reduction potential of manganate, or excuse me, permanganate, to roll that into Mn2 plus in an acidic environment? You got to look on the white reduction table. What do you get?
1.51.
1.51.
Are we gonna have the white sheet on the table?
No, you just have to know it. You have to
Yeah, you
memorize
just
the
have
whole
to
thing.
know it. Memorize everything.
I wonder if
Nothing will be given to you. Not even degree.
My bad, I should have told you that.
I think he said that 3 times, so we are going to have the white sheet.
Everybody is. Yeah,
That's a COVID question right there.
Do you see
Oh,
this
okay.
gray
I
hair?
can't do this Saturday with you.
Has Addie.
We had a powerlifting meet.
You should dye it purple, and it would really have Abby written on it.
We need you. Well, there's not even.
Okay.
Those gray hairs are mine.
Who doesn't?
So what's the reduction potential for Fe2 plus turning into Fe3 plus?
Negative
Minus.
0.77.
What is it?
Negative 0.77.
Negative 0.77. So does it want to go in that direction?
Oh wait,
No.
It starts at 0.77, but you have to. Flip it.
Oh, this is already flipped.
This is already flipped.
Okay.
These guys.
The reduction potential is 0.77. The oxidation potential is
Negative 0.7.
negative 0.77. Pay attention to reduction potential versus oxidation potential. So if I subtract 0.77 volts from that, you get whatever, 7.4,
4, yeah.
positive or negative?
Positive.
Positive. Positive 0.74 volts, which indicates what? Spontaneous. Okay. Now, even though I had to multiply the 5 by Fe2 plus times 5, do I need to multiply the 0.77 by 5?
No.
Because it's an intrinsic property. Quantities don't matter. It's not volts per mole. It's just going to happen. So now that I know I have I have a positive E naught value, what's going to be the sign of my delta G value? It's
Negative.
going to be a negative value. And I know that because delta G equals negative M F times my E naught value. So I know I'm going to have a negative delta G. My K value should be
Big.
big. You were choked up on that answer, Ken?
I almost said small. We had to.
Gotcha.
It was smooth recovery. Why do you admit to anything?
So, big
Yeah.
K value indicates what in terms of spontaneity? It's the forward reaction that is favored. Okay. So now back to the stoic. It takes 12.6 milliliters of MnO4 to titrate this and make it work out. So here's the question. Do you want to start with the 12.6 milliliters of the MnO4, or do you want to start with the molarity and volume of the Fe2 plus?
Fe2 plus.
Yeah, start with the Fe2 plus, okay? So you've got 20 milliliters, which is 0.020 liters of your Fe2 plus. So what are you going to put? At this point, it's just a big stoich problem. Now, fundamentally, what units do you want to end up with when you get done?
Moles per liter.
Of
KM or
What's
MnO4.
Fe2 plus or MnO4?
MnO4.
I want to end up in MnO4. I need moles per liter, right? Okay? So, you know the molarity is 0.15 moles of Fe2 plus per 1 liter. If I stop right now, if I don't do anything else, what do I have? Moles of,
Fe2 plus.
so I'm going to put moles of Fe2 plus down here, and then what am I going to put up here? Of MnO4. Where am I going to look to get that ratio? That's why you have to have the balanced equation. So shocking as that may be. So there's a 5 there, there's a 1 there. If I stop right now, what do I have? Moles of MnO4. But that's not what I want. I want
Moles per liter.
moles per liter. So what am I going to put down here in that last cell? 12.6 milliliters, which would be
0.0126 liters.
of MnO4. I get moles of MnO4 over liters of MnO4. Miracle of miracles, I get molarity. Could I just have gone MAVA equals MVBVB, like I did with an acid-base type thing?
No, because it's not a 1-to-1 ratio.
Can't do it. Bad. Why can't I do that?
It's not 1-to-1.
It's not in a 1-to-1 ratio. This does not work because it's not in a 1-to-1 ratio. Okay, can't do it. Let's see. For any KSP problem, okay, let's say that you want to deal with, deal with magnesium hydroxide, okay? Classic insoluble product. First off, how are you going to write, what do you need to write for the dissociation of magnesium hydroxide? Do not make this difficult.
Mg2 plus 2OH minus.
Mg2 plus 2H minus, right? So, if you were given, like on that problem, on that assignment that I just gave back, if you have two reduction equations, keep in mind, if it's a KSP problem, you need to keep in mind a couple of things. One is that if it is a KSP problem, you need to arrange those equations so that you have it in the form of the dissociation equation, okay? That's rule number one. Rule number two is your E naught value going to be a positive or negative value? Negative value. So if you don't know which one to flip, and you're going to have to flip one of them,
Flip the bigger one.
well, flip the one that you end up with a negative E naught value. Okay?
The bigger one.
When you get done with the calculation of K, when you get down with that calculation of K, what should that be? A big number or a small number?
Itty bitty.
Small. So there's certain criteria that you can tell if you got this right. And you're going to have one like this, I promise you. Okay? I promise you. So the criteria is you need to arrange them so that you end up with a dissociation equation of a precipitate. You need a negative E naught value, and you need a small k value. If you meet all three of those criteria, odds are you get it right. If those three criteria are not met, you did it wrong. Okay? Promise you. Anode versus cathode.
Redox, red cap.
1G, tell me one difference between the anode and the cathode.
The reduction happens at the cathode, and the oxidation happens at the anode.
So we got reduction here, and we have oxidation here. Which direction do the electrons move? Anode to cathode, cathode to anode.
Anode to cathode.
Anode to cathode.
Electrons move from the anode to the cathode. Which one has the positive charge, the cathode or the anode? And if you're not sure, the cathode contains a little thing that looks like a T, that looks like a plus sign. Okay? So that's the easiest way to remember that. So that would be the positive charge, that would be the negative charge. Let me see. If you have a concentration cell, like let's say for example you have 0.001 molar aluminum ions over here, and you have a 3 molar solution of aluminum ions over here.
With the positive charge.
Okay? And there's your salt bridge.
It starts positive.
So, if I gave you this, you should be able to identify the anode, the cathode, and calculate the value of E.
It's already positive.
Okay? So, let's start with the big idea. Mother Nature doesn't like this. Why?
Not in equilibrium.
It's not in equilibrium. Mother Nature says this is bad. Okay? So, if you look at the Nernst equation, E equaling E naught minus 0.0592 over N, ran out of room, times the log of Q. Let's talk about Q. Reactants over products, products over reactants. Products over reactants. Okay? So, what's my E naught value for this situation?
0.
0. Why? Because E naught means what? Standard or non-standard conditions?
Standard.
Standard conditions, molarities will be, if you have a 1 molar solution and a 1 molar solution, does Mother Nature see a problem with that?
No.
Mother Nature's going to chill out and go, I'm not going to move these electrons, everybody's cool, okay? I'm not going to move anything, it's cool. Mother Nature goes, this is not cool, because I got a big discrepancy between these two. So, Bethany, what does Mother Nature want to do with that lower concentration?
Wants to increase it.
So Mother Nature wants to increase this concentration, she wants to decrease this concentration. Bethany, what's Mother Nature going to do to increase that concentration?
Add more aluminum ions.
How is she going to do that? Just sprinkle some over the top or what?
Gonna take them from the 3 mole aluminum ion solution. I don't know. She's gonna move it from the
Kinda-ish.
anode to the cathode.
Okay, there's a strip of aluminum in here.
Oh, it's gonna take it from that.
Ah, yeah. So she's going to take elemental aluminum and turn it into what? Aluminum ions. Balanced?
No.
No. Where am I going to put the 3 electrons? On the right side. So Mother Nature wants to increase the concentration. Here's the common misconception. It's exactly what Bethany said. Oh, we're going to take ions from over here. No, it's not an option. I can't move ions across there. What can I move? I can move electrons. I can't move ions. Ions are too big and bulky. Okay? It's like, oh, we'll move the electrons. That's much simpler. So, since this is what's going to happen, is the 0.1 molar my anode or my cathode?
Anode.
Anode. Why?
Because it's being oxidized.
It's being oxidized. So this is where oxidation is going to happen, which makes that the
Redox.
anode. So over here, she wants to decrease the concentration of the 3 molar. Cooper, what's she gonna do?
Make elemental aluminum ion.
So she's gonna take the aluminum ion and make it gain 3 electrons and turn into elemental aluminum. So Cooper, this is what's happening. Reduction or oxidation? Reduction. So this is the red cat. So here's the $1 million question. Do the electrons move from the high to the low or low to high?
Right? It's not a concentration.
Low to high.
Low to.
Oh, anode to cathode, right?
Electrons. Anode to cathode. So low.
Anode to cathode, right?
Low to high. Yeah.
I'm not crazy. You looked at me weird when I said.
No. I was just looking at you weird because like you hesitated on it. Okay. So every time, where do the electrons move? From the anode to the cathode. Now this is a little bit counterintuitive because you can make the analogy like you can't make the analogy like a ball rolls downhill. The electrons actually roll uphill in this situation because they go from the low concentration to the high concentration. Let's say that you have,
No osmosis? No.
and I'm just doing this to show you the math, okay?
This is exactly what you
Okay, so this is what you're going to do wrong, okay?
Okay.
And you say you won't, but you lie. So let's say this is my cell, and you want to use the Nernst equation. I don't care what the E0 value is, that isn't what you're going to do wrong, okay? Minus 0.0592. Because zinc is 2 plus and the aluminum is 3 plus, what's going to be my value of N? 6. Now, the log of what over what? Do I have to worry about the zinc as a product? Why not? It's elemental. So it's just going to be the concentration of my aluminum ions, right? Oh, that's what you're going to do wrong.
Forget about that.
Wait.
No.
Again, you say you won't, you lie. Because there's a 2 in front of that, that has
I
to
forgot
get,
about that entirely.
and the zinc ion concentration has to get Q.
Why?
Because that's the rule.
Why is it the rule? Why is it in front of
Because
it?
there's
The
a,
coefficient.
Because the coefficient
one to one ratio.
It's known as the mass law ratio. It's a whole, don't worry about it, just accept it for now.
I can't just accept it.
Yes, you can, because I don't have time to explain it.
Okay.
Okay,
Whatever.
Wikipedia, Charles.
those are the big things.
Wikipedia.
Also, make sure you can do the stoic where you have amperage. So if you have like a 10 amp current, what does amps mean? That remember that means coulombs per second. If you're not sure, right here on the green sheet it says I equals Q over T. Okay? So don't forget that. Now, with the Nernst equation, the way they have this, they have RT-NF, natural log of Q. At some point, you need to decide whether you want to use this natural log equation or do you want to use the log version. Out of the kindness of my heart, I will give you, or write up on the board, the Nernst equation in terms of log. Okay? Now, shh, don't tell me because I'll deny it. So, if you like natural logs, hey, you can do that. You have R 8.314 times temperature and Kelvin and divide it by Faraday's constant. How you do that, I don't care. Okay, let me explain the review, because it's a little bit jacked up how I had to run this off. Okay? So, you're going to have this, the reduction of the redox to the relative requisites. Okay? So, this one's okay. The reason that I marked through question number 1, because this was a redox reaction done in the basic environment. The AP test used to make you do redox reactions in basic requirements, and they don't anymore, so that's why I scribbled that out. So everything else, here's the 10 questions, there's the answer key for that one. So that one's fairly straightforward, so that's just kind of a one and done kind of thing. Now, the next one, you got the odds and ends over oxidation and reduction. I used to give this out as an assignment, but I shifted it to the review. So the front page is pretty straightforward. This is just the blank version of it, okay? This is just blank. There's no answers on this. And I actually have that other, listen to me. Here's this other reduction chart. It's right here.
Do you think we're gonna get that on the test?
I think so, yeah.
What?
I know, shocking. So,
I'm gonna get tattooed on.
I know. So,
Tattoo, all reduction.
you're going to get 2 answer keys that go with this. So, one is the answers to the 1 through 9. The other one is going to have, where did it go? Oh, the other one is going to have, that you're going to get with it, is going to have the answers to 10 and this, because I had these on this sheet. So, the one that says odds and ends, you're going to get 2 answer keys. One that's going to have 1 through 9 on, and the other one's going to have the answers to 10 through the rest of them. Okay? So, that's what you've got. So, figure out, for those of you that are going to be leaving, whatever, how you're going to be doing that test. You're coming in straight in,
Yeah.
okay? You're going to be here.
6:45.
You guys are going to be,
7:40.
okay. All right. Okay. So Kevin, stop you on the camera. Let me hand